So let's look at nuclear transmutations. This will show you how to write equations using radioactive decay. So first of all, alpha radiation, remember, is a helium nuclei. So you write alpha, He, the isotope of helium, which has a mass of 4. Uranium-238 undergoes alpha decay. So when the alpha particle is on the right side of the arrow, this is decay. And since we're using an alpha particle, I'm going to write alpha decay. Notice that you start with uranium-238, and it decays with one alpha particle. The other particle is determined by taking away the 2 from the helium, and we know that it has to be thorium because thorium is atomic number 90. Notice that the 2 and the 90 add up to 92, which has to be the same value on the other side of your equation. So you can think of the arrow sign as an equal sign. So 92, you create an alpha particle, you determine the other nuclei by knowing the atomic number. The mass number is the same process. If we take away 4 from 238, we get 234. 234 plus 4 is 238, and that equals the 238 from uranium. That's alpha radiation. And just notice that both the total mass and the number of protons are equal on both sides of the equation. Here's another example where we have plutonium-240. This is plutonium-240. It undergoes alpha decay, and it creates uranium-236. So let's write an equation. Start with plutonium. 94 is its atomic number. 240 is its mass number. You're told it's alpha decay, so you know that He is on the other side. To determine the other particle, I take 94 and I subtract 2, and I know my product has to be element number 92. You use your periodic table, you find that it's uranium. The mass number, though, is this upper number. Take 240 and subtract 4. So 240 is the mass, minus 4 from the helium gives me 236. That's how we determine the isotope. So there's your equation for this graphic. In beta radiation, an electron is lost. So what happens in beta radiation, it's really interesting. A neutron decays into a hydrogen ion and an electron. So notice there's no charge on a neutron. So 1 plus a negative 1 gives you 0. Notice the mass of 1. Hydrogen has a mass of 1. An electron, we say, doesn't have any mass. So oftentimes we say, because hydrogen doesn't have an electron, we say a neutron decays into a proton plus an electron. So remember that E is your electron beta particle, and your H is your proton. In beta decay, a neutron decays into an electron and a proton. So another way we can, let's write that again. A neutron decays into, a proton is going to be a hydrogen, okay, and the electron, minus 1 charge, no mass. We also call that beta emission. So another isotope that undergoes beta emission is carbon-14. When carbon-14 decays, it emits the electron. And notice your 7 plus minus 1, oops, getting ahead of myself there, is equal to 6. So the 6 is on this side, the 7 and the minus 1. Notice the mass remains the same, 14. Let's write an equation to illustrate the decay of hydrogen-3 by beta emission. So first write it as a nuclear symbol. It's hydrogen-3. It says beta emission, so E minus 1, 0. So that's what you write whenever it says beta emission. Now, to determine what the element is, remember 1 has to equal 1 on the other side. So if I have minus 1, what do I need to add to it to equal 1? You could put an X there if you wanted. I'm going to add 1 to both sides. And notice minus 1 and positive 1. I have X equals 2. So 2 is the element I have. Go to your periodic table. Which element is 2? It's a helium nuclei. And the mass here, I have 3 with a 0, so I know it's helium-3. So there's the equation. Gamma radiation is the highest energy radiation from nuclear decay. And notice there's no change in atomic number, and in this one, no change in mass. This is just energy. So this ion would be more stable, but you wouldn't be able to tell that just looking at its numbers. So those are the 3 types of radiation and how to write their formulas.